Please feel free to grab a chair. Just a quick informal question, like who uses serverless today? When I say serverless, do you mean Fargate?
No.
Lambda functions?
Yes.
And what do you use it for?
Everything. Sending
Authentication.
SMSs, hosting APIs, batch jobs.
Nice. Step functions?
Yes. The developer.
Okay.
Okta
Okta.
integration.
Okta integration with Lambda functions?
Yeah.
Like with API gateway, Lambda
Yep.
authorizer?
Yep.
Oh, wow. That's my favorite topic.
Got the built-in authorizer.
I inherited a lot of stuff.
Okay. I'm just kidding.
No, it's right. Like I'm always looking at other repos going, what are we doing here? And
Yeah.
closing them carefully so that I don't break anything and I back away slowly.
You'll find one of my repository which showcases Okta integration with Lambda authorizer.
Yeah.
Great, thank you. And just to show of your hands, who is part of application teams, who is developing applications? Nice. Ops, using Lambda for glue, like just gluing operations left and right. Okay, so it's good. So that's the beauty of Lambda functions. You can use it for anything. It's a friend for application teams. It's a friend for operation team. Whatever it is, if you want to connect from one dot to another, if there is something that you can use to connect, that's a Lambda function. Has anybody used? Okay, let me ask this way. What is the most used runtime in Lambda functions? Python? Node.js? .NET? We need to talk. Okay. Java? Only one hand? Okay.
We use 3 of those 4.
We can be best friends after this session. I come back from a Java background. I was a Java developer. And there is a lot of good, cool contents coming when operating Java on serverless. How about Rust? COBOL? Yeah. Java in custom runtime? GraalVM? Okay. So I get the sense there are really good topics that we can talk about after the session. But what we are going to focus here today is understanding how Lambda function works under the hood and why it is critical to understand that. Be it for application team members who are developing apps or operations, how do you run Lambda functions at scale? As part of introduction, my name is Dhiraj Mahapatro. I'm the Principal Serverless Specialist SA at AWS. I work for global financial services customers. So you name any big financial services customers here. JPMC. Okay. She's my customer. When it comes to serverless, you can ping me anytime and we can talk more on serverless.
Are you at Columbus?
I live in Columbus, but I have never been to the JPMC office in Polaris.
You can come.
Yeah, definitely. Yeah. We should do that. We should do that. Yeah, I'm based out of Columbus, but recently I've been traveling a lot. In fact, I was in LA yesterday. I had a red eye, and if I fall down while speaking, you know why that happened. So what we are going to cover today is actually understanding the execution environment in Lambda functions. Why is that critical? It's different than how you operate on Fargate or EC2 or ECS or EKS. We'll start with basics, how Lambda functions work, what is AWS Lambda, the invocation modes, most importantly, the execution environment, And that will help you understand how Lambda concurrency or Lambda scaling problems can be handled. And then we'll see some notable features and finally some best practices which will help you write your Lambda functions. So this is pretty simple. You must have seen this multiple times. When you are dealing with Lambda functions, events are treated as first-class citizens. Lambda functions, they only understand events. Anytime you make an API call from API gateway, it's an event. And that event is understood by a Lambda function. And no doubt there is some translation that happens in between. You get the payload as an event object with some context, but it's always an event. And then everybody is aware here that we have multiple runtimes. That's just a syntactic sugar of how you can build your handler functions like Python, JavaScript, Java, Golang, or you can bring your own container images also. Right now, you can have zips as well as container images where you can bring your own runtime and also package it as images and you can run it too. And ideally, when you build functions, you integrate with other services like AWS services or databases. So that's how normally Lambda functions work.
Question.
Mhm.
So how many customers do you see running their own website? In common, is it not?
It is not common yet, but we have seen enthusiasts who want to run Rust. They can bring their custom runtime Rust and run it. What I'm trying to work with customers too is to understand how they can bring custom runtime when something like Graal VM as a native image you want to run it. Right now, there is no direct native image support as a runtime for a Lambda, so it has to be a custom runtime. You build an image, it can be Graal VM specific or anything specific to .NET, a native image, and you have to run it as a custom runtime. But to answer that to your question, I'm working with financial services customer who understand the benefit of bringing native image, but the trade-off is more maintenance, like patching and so. So this is what you see when you run Lambda functions, right? As a service, the big yellow box is the Lambda service. The services icon on the left, they are the ones triggering Lambda functions, and then multiple ways of triggering. So you have API gateway, SNS, DynamoDB streams, etc., Kinesis, and then once you have event triggering the Lambda function, you have the Lambda service downloading your code from the repository, either an S3 bucket or anything. It gets the zip file, gets the layers or the container image, figures out what are the configurations for that Lambda function, and then it figures out what is the execution environment that it should pull to make sure that the event that is coming in or the request that is coming in has to be handled. And all of this happens in a matter of seconds if you're using a runtime which doesn't give you a large code stack. If it were Java, you will see a higher code stack because it has to bring all the classes in the memory, it has to load the classes, and then with the execution environment. At the same time, IAM execution rules are also applied. Also, the function policies are evaluated, making sure that a service that is not assigned to invoke the Lambda function is not actually invoking it. So all those controls are in place. And on the top right, you will see like aliasing, versioning of Lambda functions, everything is taken care of. So this is what happens when you invoke a Lambda function from either of the service. What happens under the hood, the Lambda service itself, is based on your invocation type, whether, and we'll talk more about the invocation modes, async, sync, and even source mapping. You immediately see a front end, which is the orchestrator, in this case, which is handled by Lambda service. That front end is responsible for taking the calls or the events that are coming in and making sure the worker environments are ready and wake up a worker environment and make sure the handler function is called in that worker environment. Now, you also see there are two components here, internal queue and event source mapping. We're going to talk about it in future slides, but let's dive deeper to understand what are the invocation modes. There are mainly three invocation modes. One is synchronous, that you already see mostly when you are integrating with API gateway. It's a request response. So the caller sends a call to API gateway transforms and triggers Lambda function with an event payload, and Lambda function has to return back a response within. Can anybody tell me what is the max timeout of API gateway?
15 minutes.
Yeah.
API gateway,
30 seconds, 29 seconds.
29 seconds. So 15 minutes is for the Lambda function. So even if you have a max timeout of 15 minutes in Lambda function, API gateway will time out at 29. So write your functions in such a way that you return back a response within 29 seconds. And in this case, you also have to handle errors as a caller, since you cannot retry inside the Lambda function itself. So as a caller, you have to handle errors. Then we have asynchronous, where the caller actually doesn't expect a response back. It's fire and forget, and that's where the internal queue comes into picture. We'll talk about that in detail. And then event source mapping. Event source mapping is kind of interesting because it is per service basis. Let's say you have Kinesis data streams, DynamoDB streams, or SQS. Each one of the services have their own event source mapping when you're setting them up to trigger Lambda functions. Underneath, they are still synchronous, but the event source mapping itself is designed to work with the corresponding service that is trying to trigger a Lambda function. Let's talk about synchronous. In all of those cases, like in all those three modes, you'll see the front end is being hit first, and that takes care of routing and figuring out which execution environment or how execution environment to be provisioned by the service. In this case, like if you're looking for immediate response like API gateway, front end will figure out what is the execution environment, pick up the sandbox, run the micro VM. In this case, it is Firecracker, provisions it, and then make sure the API is actually going to the backend Lambda function. If you see there are multiple calls, or if the concurrency, or sorry, the throughput or the request per second to that particular API gets higher, then Lambda as a service will start throttling it if API gateway is not throttling it at all. So you'll see some throttling at the Lambda service layer. So you have to make sure if you're building APIs with the Lambda as a backend, your API gateway is built in such a way that it should be able to handle increasing RPS. Then we have asynchronous invocation mode. In this case, again, let's say you have SNS topic and Lambda function is set up as a subscriber to that topic. That call is asynchronous, so SNS fires it, it waits for some acknowledgement, but then it forgets about any response coming back from Lambda function. Whenever the request comes in, the front end will immediately put that in an internal queue that is maintained by the AWS Lambda as a service. And then the micro VM or the execution environment picks it up from the queue and starts executing the request. The internal queue can process these events or messages for up to 6 hours, and it supports two retries and 3 invokes altogether. The good part with asynchronous invokes is that you can set up Lambda destinations and DLQ. Now, Lambda destinations is a whole different topic, but in short, for any asynchronous invocations to Lambda function, like let's say coming from Kinesis data streams, DynamoDB streams, SQS, SNS, you can define destinations saying, if there is success, if the Lambda function was successfully able to execute the logic, on success, I want to do something else. It can be invoking a different Lambda function. It can be putting an event in Event Bridge, or it can be putting a message in SNS topic. The same thing you can do on error. So it's like a callback, but it's not callback actually, it's on success or on error. You should be able to do multiple things. And that is only possible for asynchronous inputs. Then we have event source mapping. Event source mapping is like it's an entity inside the Lambda service itself, which will start polling for messages. This is applicable for SQS, even with Kinesis data streams or MSK. You define the batch size. You can define a batch size of how many messages you can pick up from that particular service. And you can also define the polling interval. Like, do you want to do a long poll or it has to be immediate? You can all define in the event source mapping itself. If you are using Kinesis data streams, you can also define the parallelization factor as to how many Lambda functions should be parallelly getting invoked per shard per Kinesis data stream. So all those settings are all available in ESM. Event source mapping, I call it ESM. It's a normal way to use. You can handle errors. It also comes with DLQ mechanism, and the particular capability of ESM is defined by the service that you are using.
Can you define DLQ?
Dead letter queue. So after multiple retries for your Lambda function, if it retried, but it still has to deal with an error, one way to bail out of that continuous retrying is to put that message, put that entity, or put any kind of entity in a dead letter queue, so that any other entity or any other party can come and read from that dead letter queue and start gracefully handling that. Yeah. Thank you. Oh, just in case for the recording, the question was, what is DLQ? DLQ is dead letter queue. Any questions before I move on? Yeah.
So you have an asynchronous and asynchronous call to the same Lambda. Does the synchronous call overwrite in terms of have a limited number of executions per lot at a time from the queue that will get priority over the
So the question is, if you have asynchronous invocation and synchronous invocation to a Lambda function, will the synchronous call be prioritized over the asynchronous call? The synchronous call, it depends on the availability of the concurrent Lambda functions. If the Lambda functions are working inside the concurrency limit, you would not see the priority, but a synchronous call should, it's a direct call from the front end to bring up the worker environment, whereas the internal queue gets populated, which gets polled again. So you will see synchronous response being handled earlier than async response. But if you try to go to that level of metrics to figure out, you can try that, but I have not personally seen that behavior, like which one runs first. It all depends on the availability of concurrent Lambda functions. Any other questions? Okay, so we talked about invocation modes. Now let's dive deeper to the right-hand side of execution environment. And this is very critical to understand. Why this is critical? Because every region, like US East 1, US East 2, they come with a default limit of how many concurrent Lambda functions you can run. No doubt they are soft limits, but understanding how it works will help you build your applications and apply best practices so that you don't need that many higher number of concurrent Lambdas running at a time. So this is where your code runs. So if you wrote a Python Lambda function, whatever you have inside your handler method is exactly what will be run in your execution environment. But a lot goes behind making that execution environment up and ready until you actually invoke the handler method. And the most important part is the last line here on the first bullet point. One execution environment handles one request at a time. So you have execution environment is nothing but an EC2 instance. You can bring up, like the Lambda service brings up an EC2 instance. That doesn't mean that more than one Lambda function can be handled by that execution environment at a time. It's always one handler method running in one execution environment at given point in time. And that is very critical to understand to handle concurrencies. Because when it comes to concurrency, the number of execution environments that are actively serving the traffic for a given function per version per alias is driven by this method, this formula. So the concurrency of Lambda function is the requests per second that are coming in times the duration the Lambda function takes to execute, or the execution environment is busy executing the handler method in seconds. So if you think about it, if you keep the request per second constant, let's say you are getting 1000 requests per second by API gateway and you have a Lambda function. If your Lambda function is taking more than a second, then you need 1000 Lambda functions actively and concurrently available to handle all those 1000 requests. That might not be easily available for you because there will be other Lambda functions per account that are actually using the execution environment. So this makes it clear to understand why it is very critical. Let's say the yellow line at the bottom is the time, that's the x-axis. And let's say a request came in, let's say this one came in, the first one. It's an API call that came from API gateway, and a Lambda as a service went to the front end, and now a worker environment is up and running. So we have an execution environment. You see a huge block called initialization, because in this phase, Lambda service will bring up the execution environment, download the zip archive of your function, unpack it, start the initialization code, like whatever code you have above your handler function, all the initializations, they're all done, after which your handler method will be called, and that is your invoke, right? So all of those things happen, and you have your invoke method or your handler request. Now, while this invoke is being done, this execution environment cannot have another invoke here, right below it at the same time. It has to be after it. So this matches with what we just talked about. An execution environment can only have one handler request method running at a time. So in this timestamp, if you draw a line from here to here, you can only have one rectangular box, which is invoke. You cannot have more than one. So the execution environment is busy executing this request. Let's say the request is complete here. Now the execution environment is up and running. Oh, go ahead.
I just want to point out, we can't see there.
Oh, I'm sorry. So
You just point up, I think.
okay. So the first execution environment, the block on the top, what you see, we have initialization that has to happen first. And then the invoke box that you see on the top, the first invoke box, if you draw a straight line from that to match this x-axis, you'll always find one such block in an execution environment. You cannot draw another invoke block right below it. So an execution environment should only be executing one handler method. You have a question, sir?
So that means that if you have start then if you have two functions that like right at the same time, then you're going to pay a penalty of the slow start.
Yes. So the question was if you have a function which takes more time to initialize, if the initialization block is a little bit bigger, and you got two calls, that means you actively need two execution environments to handle those two requests. You're absolutely correct. So in this case, you have one execution environment ready, and the first invoke is called. And then the moment the first invoke is complete, that execution environment is warm and initialized. Another request came in, the second box in the right, you see the second box after the first invoke, that is executed. And another request came in, which is the third invoke, but at the same time, a fourth request came in too. So the 1 and 2, they came in serial, but 3 and 4, they came in parallel, which matches to your point, right? So if 3 and 4 came in parallel, so look at the third box of invoke in the topmost rectangle, and fourth one in the bottom. Since both of them came at the same time, the fourth request needs a different execution environment because the first one is busy. So you have to go through the same cycle of initialization. That means it will download your zip artifact, it will unpack, initialize your code, and then you can invoke. Now think about this at a scale. What if 100 requests comes in and you need that many execution environment? So what matters the most is how smaller you can make those blocks, the initialization block and the invoke block. Yeah.
On your timeline, there seems like the initialization there on the bottom should be underneath the third invoke on top.
The initialization on the second execution environment,
Right.
yeah, it's separate from the first one.
Right. So when you're showing kind of in a timeline, wouldn't that initialization be under the third invoke on the first row?
Splitting hairs now.
Oh, okay. I understand what you mean.
Yeah.
So if the initialization is happening here, that means the request came at this time.
Yeah.
Yeah, you're correct. So while, yeah, you're absolutely correct. While the first execution environment is actually executing the first invocation, the request came in and this execution environment has to be ready to handle that request. So you initialize a new execution environment. So again, think about it at scale. So if your boxes, if the invoke box is wider, that means your execution environment is busy executing your Lambda code. That means you need more and more execution environments when requests come in. So that best practice is to make sure that invoke box is as small as possible, as thinner as possible, so that your execution is complete and that execution environment is available to pick up the next request. That way, overall cumulatively, your concurrency will go down. So this is how it will look like. I'm sorry. I'm sorry, I can't hear you. Yeah, that is done by the Lambda service. So the question was every invocation, if the execution environment is not available, a new EC2 or a new execution environment is made available by the Lambda service. Yes. So if you go by this formula and keep transactions per second constant, then your duration is directly proportional to concurrency. If your TPS is 100 and the duration is right now half second or 500 millisecond, then you'll end up with 50 concurrent. You will need 50 concurrent Lambda to handle those 100 requests. But at the same time, if you added some code to your Lambda function, added new feature, and suddenly that half second became 2 seconds, then you need 4 times that many Lambda functions to be concurrently executed. So you can understand how critical this is. So the bottom line is you optimize to make sure the duration is less than a second, and you can start monitoring the concurrent executions. And that's where the best practices come into picture, like make sure your initialization of the clients, like if you're talking to DynamoDB or Secrets Manager or SSM parameter store, they're all outside your handler function so that you can initialize it only once and you don't do that every time a handler function is invoked. There are more that will need a different discussion, like all the best practices, what you can easily implement. But if I want you to take away one thing from this session is keep this in your mind. If your Lambda handler method goes away from 500 millisecond or half a second to 2 seconds, then at the constant rate of TPS, you will need 200 or 4 times that of concurrent Lambda functions that you were using.
One question. So the reason I need to be concerned about 50 versus 200 is purely from a performance reason, right? Because the cost is not a factor because EC2 or the worker thread are by AWS, right?
Now, the cost of a Lambda function, the pricing is based on how much time do you execute a Lambda function, like the function itself, GB per GB second. So what is your memory configuration and how long is your Lambda function is executing? So in this case, if it is taking 2 seconds, then you will be charged for
that much
2
time.
seconds, 2000 milliseconds.
Thank
It used to be 100 millisecond as a unit. Now it is 1 millisecond. So you'll be charged on a 1 millisecond increment.
Thank you.
Now to handle some of those, like how you want to optimize your Lambda function so that it behaves better, there are some open source tools. Like this is power tuning. You can use this open source tool to figure out what would be the optimal configuration of your memory so that you get a good price and performance point. And you can decide what would be a good point because your memory configuration is directly related to the CPUs that you get. If it is 120 MB compared to 10 GB, if you use 10 gigs, you get 6 vCPUs, but you might not need full 10 gigs and you'll be charged for that. So this is a tool to figure out, if you see this graph, there's a blue line and the red line. The blue line is actually the execution cost and the red one is the execution time. So you can figure out what is the sweet spot and you can pick up the underlying memory configuration for your function. Also, to understand Lambda performance, like Andrew mentioned in the previous call, like you can have some CloudWatch queries like this, where you can figure out what is the cold and the warm start, not just average, but starting from P50, P90, P95, P99, and max. This will give you a good number of how much time is spent during the installation, and then you can optimize based on that particular metric. This is pretty new. There are 2 architectures right now available. It used to be just x86, but now you can use Graviton 2, which is ARM64, and you can get up to 90% better performance and 20% lower cost. So if you are creating new Lambda functions, try out Graviton processors and see how it works. There are a few things to keep in mind is your binaries that are you using for your Lambda functions should be compatible with ARM64. So in normal use cases, it should be possible, but if you're doing some heavy lifting like image processing and video processing, which uses particular libraries that are not ARM64 specific, then you will run into some issues. But start with the normal use cases. Other notable features like recently released Lambda function URL. This is something you can try out. So this is the configuration. When you create a Lambda function, you can just configure to have a publicly available URL, which you can directly hit from outside publicly, and you can invoke the Lambda function. So this is a good way to bypass API gateway if you have a small feature that you can just publicly make available in Lambda function. Yes, sir.
Proxy connection between gateway and Lambda, or?
No, it doesn't use.
I mean, in terms of the data that ends up.
Yeah, that's exactly correct. Yeah. So if you are sending HTTP payload, you can directly use the API gateway request and response schema, and you will get the same behavior. So if you have a Lambda function that is actually integrated with the API gateway, and if you are using the API gateway request response, you can try to test it by just removing the API gateway and configuring this Lambda function URL and start hitting the URL that is generated for you. Other notable is now you can have up to 10 gigs of ephemeral storage, which used to be 512. Recently released first week of April. So it's a good use case for where you have big files that you want to process locally instead of going over the network and fetching it from EFS or S3. You can put them in your temp storage and start processing. It used to be 512, and any increment above 512 is an additional cost. Up to 10 gigs you can use. Others are normal, like you have EFS integration, RDS proxy. If you want to integrate with or call RDS database, I would highly encourage looking at RDS proxy so that you don't run into connection pooling issues and code signing. Best practices here, again, concurrent executions are based on regions. You also get a burst capacity, which is a hard limit. Important to note that if you are integrating with API gateway, you get a 6 MB limit for synchronous calls and 250 KB for async calls. The deployment package size, the good thing is you can have a container image up to 10 gigs. One of the good example of running container image on Lambda is if you are training your models, machine learning models, you can train them in like on-prem or internally wherever you want, or SageMaker. Once it is trained, fully trained, you can package it in a container and you can have an inference endpoint in Lambda function. I think we covered most. We also have tools like Lambda Power Tool. I would highly suggest using them if you're building. It is available for Python, Java, and recently started with TypeScript. There are some cool abstractions that are built over logging, metrics, and tracing. So you start using them. Error handling, we did talk about. If it is synchronous, you have to handle, the caller has to handle. Otherwise, you start using Lambda destinations or DLQ. For function optimizations, you try to reuse the initialization phase as much as possible, because when Lambda as a service initializes your function, it doesn't rely on the memory configuration that you have set up for the function. It actually gives you a burst of memory and CPU. So you can do a lot more during the initialization in that burst compute and memory than doing that in the handler method, where it will limit itself to whatever you have specified in your memory configuration. Obviously, minimize the size. Yeah, I'm sorry.
You also said keep the initialization very small.
Yeah. So, yeah. So the question is, I said keep the initialization blocks as small as possible. It means that you don't have to load classes that you don't need, remove libraries that you don't need. So you try to keep it lean. And if you use something like GraalVM for Java runtimes, it does it for you automatically. It kind of does a tree shaking inside, and it removes the binaries or the classes that are not needed and packages the ones which are only needed. But if you're not using native image, try to remove unwanted dependencies, which doesn't make any sense for that particular Lambda function. That way your package size will be smaller and your initialization will be faster.
Sorry, what did you say? Does that for Java?
GraalVM. GraalVM is a, you can look it up, it's from Oracle. It's a polyglot VM where you can compile application code to native binaries.
Question.
Yeah.
How do layers transform into that dependency?
That's a good question. How does layer transform into that dependency? If you see there are dependencies that are being used by multiple Lambda functions, you can definitely put them in layers.
Does it reduce your initialization?
Yes, it helps. Because it is not packaged inside the Lambda function, that means when the execution environment comes up, it doesn't have to worry about unpacking and bringing them up, but it goes in the layer unpacking phase. So it's better to use layers whenever possible. Again, we have serverless lens for well-architected framework. Look at those questions that is there across all 5 pillars. And serverless rules as an open source, it's like a linter. When you have infrastructure as code, you can validate that function has tracing enabled or not, and then you can stop provisioning your infrastructure. It's like if you are into Jacoco in Java, if you are trying to do some additional checks while you build your Java application, similarly, you can do some more stuff when you are actually trying to build serverless or provision serverless architecture. This is the main part I was trying to reach to. We have done some sample applications across different runtimes. And the one I'm focusing on right now is the top right, which is Micronaut, Quarkus, and Spring Boot. We have the sample application to showcase how does it behave if you would run them in managed runtime, as well as using GraalVM native image. So there is a benchmarking table where you will see how it performs, how the architecture performs if it is packaged as a GraalVM native image. I would also suggest you to take a look at the .NET sample. There are examples of using .NET 3.1, .NET 6 Core, and corresponding native implementation of them. And by far, .NET has performed way better than Java. So you can take a look at the metrics. And Rust is at the top. If you look at performance, with Rust, we also see some microsecond performance. So Rust is at the top. Yeah, with that, it ends. But please reach out to me. My Amazon email address. You can reach out to me via Twitter, LinkedIn. And if you have more questions on serverless, mainly Lambda functions or step functions, or all the messaging services, I'm a huge proponent of building event-driven architecture when I talk to customers. So reach out to me if you want to learn more about